Hello, good morning to all of you. This is day two of this Gyan workshop of 5 days. We will have multiple things to do today. In the morning, we will have flood related discussions. Although the syllabus or the agenda will tell you that we will talk about extreme events, I think I introduced all the terms of extreme events yesterday using that WMD report and also down to earth report. Probably you can access the material that I will provide later on for the details. The extreme events that we focused yesterday to introduce are heavy rainfall events causing floods. And I talked about drought, introduced the term, but we have not gone in depth. We will do that tomorrow. And today we will mostly focus on floods. First 2 hours with 1 hour on uh, general settings for flood studies, and then in the second hour I will show a video, little bit of that video because it's a long one. I'm not sure whether we will have time to see all of it, but that's a wonderful video for you to know because it provides a combination of drivers that causes floods, and prediction of floods is an important thing, not just for the US or the Europe, the examples that we will see, but it is very much relevant to the Indian conditions, particularly relevant to places like Kerala, where we have mountainous watersheds, complex terrain, and then heavy rainfall induced landslides. All of those things are really addressed very nicely in that video. It's about 50 minutes, but I don't think I can show all of it, but we will skim and scan a couple of important segments of that video in the second half hour. But in the beginning, I want to at least introduce the term floods to begin with. Today's learning, of course, objective is primarily to talk about how to model floods, how to. So I think you can hear me okay, right? No difference between that versus this, I assume. So we want to really start from again where we left yesterday, talking about climate change, and then we will focus on floods. But when we talk about climate change, the other term that we normally introduce is climate variability. There is a difference between climate variability and climate change, which I have to introduce to. The term climate variability and climate change, we want to really understand, right? So, and then I'll show a simple graphic where we see the difference. One is about long-term periodic cyclical change is climate variability. Climate change is the future projections. How, with respect to the past, the things are changing in the future is the climate change discussion. Hydroclimatology is the intersection of hydrology and climatology, primarily talking about precipitation, evapotranspiration, interception, soil moisture storage, groundwater storage, and stream flow. These are water budget components of hydrology. I know some of you are having non-hydrology background, particularly with computer science or other disciplines. So I wanted to really introduce these things because everybody will be on the same page by talking about hydroclimatology and water budget. That reminds me of showing a small video also on that. I'll show that. Hydroclimatology provides a perspective for analyzing water resource problems for current and future. So when we talk about the fast moving water, that's floods. When we talk about climatology, it's the amount of water that's available or stored in the system that we want to be taking advantage of for multiple purposes. Water supplies for drinking, right? And then for irrigation, hydropower, navigation, and all the other industrial, commercial, business uses. So we want to be really understanding on an annual scale or a decadal scale of how the storage changes are happening and how can we improve water management strategies. For that, hydroclimatology is very important. Now let's talk about the terms, weather, which is basically ranging between few hours to few days maximum. And then seasons, they normally talk in terms of months. Yesterday we talked about pre-monsoon, monsoon, and post-monsoon, right? Jan, Feb is pre-monsoon, or sorry, winter, and then March through May is your um, pre-monsoon, and then June through August or September is your monsoon, and post-monsoon is October through December. So those are the seasons on a monthly time step, right? And then we talk about climate variability, which can be for years to couple of decades, mostly. They talk about variability in the past. And then climate change, when we see with respect to the past, how things are changing in the future. So people kind of mix up these terms sometimes. They say climate variability, climate change, and those are two distinct, different terminologies that you should remember. When you're using climate variability, always assume it's for the past conditions. And when you're talking about climate change, it's for the future conditions, okay? Um, and then, of course, scale considerations. Land atmospheric interaction. It's a big topic by itself, but we are not covering that here. But a little bit here and there, I will introduce the term. Um, the land surface with vegetation, urban areas, agricultural lands, or forested areas, all of those things combined, forms the biomass or biosphere area, right, on the surface. The atmosphere is anywhere from the land surface all the way up to 10, 15 kilometers into the atmosphere. And then up to 50 kilometers, of course, you have all these, different spheres that we have: troposphere, stratosphere, mesosphere, things like that, all the way up to 50 kilometers. But land atmospheric interaction changes in every location. How the land communicates to the atmosphere and how the atmosphere is communicating to the land is a very dynamic process on a daily basis, on an hourly basis in some places. So that interaction is very complex, and we need to understand if we want to understand weather and climate. Spatial scale, vegetation, height, topography, precipitation cells, cloud affected radiation are all used on a bigger scale, right? And then nonlinear relationship is also existing. It's not that, what we have today most likely will be there tomorrow, but you cannot extrapolate as a linear interpolation or extrapolation in this case. Same way, if you're talking about precipitation that falls on the ground, gets into the soil, and recharges the groundwater, the flow of water that happens is highly nonlinear, very nonlinear process. And you cannot say this amount of rainfall that we got, so this amount of rainfall will be going into the soil, and then the remaining goes into the on the surface. It's not easy to divide like that. But we normally simplify the process in hydrological modeling and do that. But the scale interactions, both space and time, is very important for us to understand bigger scale process, how is coming to a smaller region and how it's impacting the local scale. So the dynamical interactions between scale and time is very, very important. Yesterday we talked a little bit about spatial downscaling. I hope everybody finished the assignment or the labs yesterday, right? So those who did not finish, of course, you can still, keep the material, and when you go back, you can continue working on them. It's an example of how we talk about spatial downscaling there, but temporal downscaling is also an important factor. Sometimes, these models produce us daily time step, but we need hourly. We need sub-hourly, sometimes 15 minutes for flood modeling. So you have to downscale them in different ways. But I'm going to actually, before I talk about the water cycle as a process, I wanted to show you one small video here. If it comes through, let us see. I had some issues yesterday with that, but we will see if it's possible today. There is no audio there. We can just project, but do I need to show this to our remote audience? One second. Excuse me. Is this to be shared to the audience remotely? Can we do that? Or is this seen by them already? Can they see? Okay, good. Okay, so just watch this, less than 3 minutes of video, no audio here, but it talks about the water cycle process. When the sun rises, what happens on the landscape, and when the rain comes, what happens to the land surface. It's a very simple illustration of water cycle. Many of you are familiar, those who have taken hydrology class, it's really a basic stuff. But for some of you who are really new to the topic, you will really appreciate what I'm showing. So the sun comes in the morning, right, every day. It heats up the ocean, we all know that. So it heats up the land mass, evapotranspiration or water vapor that goes into the atmosphere, and then forms as clouds, right? And the wind, the circulation pattern that's having around the world, will move the clouds to the land mass. Over the land, it really passes, and then when it comes over the mountains, it rises. It's the orographic elevation of rainfall, and then it dumps rainfall. Depending on the elevation, it can be rain or it can be snowfall. You know, if it's at the higher altitude with the below freezing conditions, the raindrops become snowflakes. But ultimately, it reaches the ground and then it goes into the groundwater, part of it, and then part of it is actually entering, of course, into infiltration, the unsaturated or vadose zone, they call here, below or before this saturated zone. But then, after infiltration, after deep, groundwater recharge, part of it is actually entering into surface runoff systems, including the small creeks to rivers, and then, of course, it finds its way all the way into the ocean. So it's a very simple illustration of different components of hydrologic cycle or water budget. So this partitioning, what we are talking about, precipitation into evapotranspiration or evaporation, if it's combination of transpiration and evaporation is called evapotranspiration, and some of you are familiar. If it's coming from the vegetative surface, it's transpiration. If it's coming from the water, it's evaporation. The combination term is ET. It's a big term, right? So this cycle happens on a regular basis, right? This happens from morning to evening in different places, and it changes depending on the terrain, depending on the land surface, depending on the latitude, location on the planet. So when the sun sets, of course, the whole thing shuts down. So it's a 24-hour system. Like human beings, the planet Earth strongly interacts, between the land and atmosphere, and it creates this whole, cycle on a daily basis, and it changes even by season. The same amount of rainfall will not fall every place in every month, and again, it changes depending on the month of the year, right? Some places you don't get rainfall in any time in the winter. Some places you get rain. So all of these things are to be understood when we are talking about hydrologic cycle and water budget components. So I'm going to stop that here, and then let's look at this slide back, because I will refer to these terms again and again. So at least now when I'm talking about the water cycle components, you understand that there are, when we talk about spatial scale, you understand the mountains versus plains, and then the scale, temporal, morning versus evening to seasons to decades and all that. So these fluxes, what we call as fluxes, moisture flux, heat flux, all of those fluxes that we model in the system are considered constants and treated deterministically in some instances. In some places, they are also coming up with the probabilistic based approach. So watershed scale variability is very substantial, as we all know. Not every place within the watershed, especially places like Kerala, you have such a variability with respect to landscape, with respect to vegetation, with respect to atmospheric conditions. So there is some level of uncertainty. Yesterday in the afternoon also, you heard from the speaker about how that stochastic nature is coming into play, right? So global climate is very dynamic. It is constantly changing, both from the internal and external forcings. Both climate change and variability is impacted by that. Active forcings, now when the sun comes, of course, kind of actively changing and creating some instability in the atmosphere. And of course, it's dynamical depending on the location. In the latitude regions, like equatorial regions like India, you have a strong connections. In some places, you don't have that strong active forcings. Passive or stochastic in nature due to random evolution of certain systems within the Earth system is also there. So these active and passive systems are dynamically modeled in these models. Again, I will talk about floods today, so I'm going to skip here for some of these drought related examples for now. Just hold on your thoughts. We talked yesterday about GCMs and downscaling yesterday. So again, these are needed to bring down the scale. The reason why we are talking about scale issue, as you know, yesterday we talked about these GCMs or global circulation or general circulation models. They model this planet Earth on a grid by grid basis, both horizontally and also vertically over time steps, right? So there are, four components what we are talking about: X, Y, and then vertical Z, and then time T. So four elements or variables are involved in modeling the whole Earth. So they cannot go really at high resolution of 10 kilometer. It will be computationally very challenging. That's why they run the model at 1 degree, half a degree, or 50 kilometer, 100 kilometer, something like that. But then we are taking those model outputs and downscaling. That is the purpose of doing the downscaling, right? And of course, global warming, as we will see more today, with the flood literature, more evaporation is happening, and that actually causes amount of precipitation to be falling on the ground. More ET means more evaporation, or sorry, more rainfall. Roughly, when we talk about water budget, let's say 100% of rainfall falling on the ground, 60 or 70% of it is going back as evaporation or transpiration. The remaining only flows on the ground. So that partitioning changes again from place to place. Precise partitioning is very, very important if you want to really understand how the runoff will happen and what is the availability of water for a given location, right? Something like that. And then there is also, we'll talk towards the end of the lecture today about the ocean circulation systems. And the primary driver of ocean circulation and how things are changing on the land is driven by sea surface temperature. The temperature of the sea taken over the long-term average is the sea surface temperature. If the surface is warm, sea surface temperature is warm, it produces more water vapor into the atmosphere, right? And then the atmosphere is already warm enough because of climate change and increasing temperature. They take all this water vapor into the system, and then it brings down heavily on the ground, so as rainfall. So this is the repeat of many times that we will see today with examples of climate systems. And there are two other things I want to introduce here. One is called climate of the first kind, and then there is another one called climate of second kind. The first kind is, of course, is the one that people started with back in these early 19th century. They say everything is driven by climate. So the earth was considered as the recipient of this climate system. So there is no linking between land and atmosphere. There is no connection between biosphere to climate. That was the climate of the first kind period. But then it became climate of the second kind, where they said, no, no, you cannot really ignore land surface. We have to consider them as an integrated system. So that happened. That realization came in around 60s, 1960s, 70s, and then for the last 50, 60 years, the significant advancement with respect to weather predictions and climate predictions are happening because of this recognition of climate as the second kind. And that recognition, of course, is improving day by day with more and more data that we have. And of course, unless we recognize that, the non-linearity part that what we are talking about between these systems is not going to be easy to predict. So that's why we are seeing the climate system to be integrated. General notion is that atmosphere is less chaotic, which is not true, right? On a regular basis, if you see even few hundred meters to all the way up to top level of the atmosphere, wind circulation is happening all the time around the year across the planet, right? And that is very chaotic depending on the location. And uh, to model that is, of course, is very, very important. And atmosphere has got such a short response time. Basically, it cannot hold moisture. When the moisture laden clouds are forming, it has to dump that amount of water onto the ground. Where it falls and how it flows is a different story. But depending on how the circulation patterns are bringing that moisture into the atmosphere is very chaotic and very active in a way. And because the atmosphere is having low specific heat capacity or holding, heat capacity, it makes it very volatile for that reason. The opposite is true for the ocean. Ocean has got a very slower circulation. Things don't change that rapidly. But when they show the signs of warming, you can clearly see that it has accumulated over time. Ocean heat content that we talked about yesterday, from surface all the way up to 700 to 2000 meters below, very actively changing, but not as fast as what you would see in the atmosphere. This is all created, by the nature already. So the mass of ocean is greater than mass of atmosphere by 280 times. So the specific heat capacity of ocean is much greater than the capacity of the atmosphere, which is about 1200 times. So you can understand the retention of heat in the atmosphere versus ocean, such a big difference, right? 1200 times of difference. So that plays out very well for us in terms of seasonality, in terms of keeping the place livable, bringing moisture from the ocean, all kinds of things that's happening because of this, mass concentration difference. The response time can be anywhere from weeks to months in the top 100 meters to centuries and millennia in the deep ocean. Sometimes it takes hundreds and hundreds of years, thousands of years in the ocean to change. But on the land surface, it's pretty quick. It can be, especially in the top 100 meters or so, can be very active, very quickly changing systems. Okay, so I'm going to skip all this because these are basic stuff anyway. There are 5 spheres that we have, right? Cryosphere, yesterday we talked about Antarctic, Arctic ice system. Lithosphere is the soil column. Biosphere is the one that we have vegetation, land mass. And then atmosphere is the one that I talked about just now. So uh, these combinations of spheres really makes the whole place interesting to live. Earth is located in a place called Goldie's Lock, where the sun is actually hitting at the right angle, correct angle, and then we are talking about use of that energy, heating up of the planet, and then of course use of that energy for everything, right? Renewable, non-renewable energy, that when we talk about yesterday a little bit. But essentially all of these systems are having one common thread, and that is water. And water brings you and me together in this classroom all the way from my place, because we are connected in some form. The destiny, like I mentioned in my talk yesterday, the ultimate thing about the whole planet Earth, whether or not it's livable, is determined based on the availability of water. Just to give you an example, NASA, when they sent the Mars space rover, um, what did they try to find out first? Anybody recall? What did they try to find? Signs of water. Yeah, there is no, liquid water right now, but they wanted to know, was there water there before? Did they all dry out? Did they all evaporate? And that's why we see that as a red planet, dusty, no, place to live, very hot, all kinds of things. Specific heat capacity is very less because of the atmosphere is so thick with, air column. There is no heat that can be retained. No water means there is no, capacity, heat capacity, right? So the first sign of a place, whether or not one can live, is determined based on the availability of water. So how important for us to preserve, to conserve, to create surplus based on the rainfall that we get is an important thing that you should remember. Again, the small portion of the available water is only fresh water. 70% of them are, again, taken into the rivers, lakes, and groundwater systems, primarily for irrigation. Essentially, this is an important statement that you all need to remember. Supply is not equal to demand, right? It's like our earning, let's say, monthly earning. You make certain amount of money, you have a budget, you spend it, right? So that's the individual finance management, right? Same way, water management is determined based on the supply and demand. How much we get from the atmosphere as a supply, how much we need, how much we demand, whether it's for day-to-day purposes or whether it's for agriculture, for hydropower, municipal, industrial, commercial use, or navigation or fish flows, environmental flows, all kinds of needs that we have. So to quantify the demand is an important job. Civil engineers, hydrologists, water managers, planners, decision makers need to know what is the demand for a given location, given watershed, given river basin. And then based on the supply, you then divide that. What kind of demand that you can be met with. That is the thing. And that is a field of itself, having plenty of scope. It's not fixed, it's not constant. You don't determine when you get the rain, right? It's nature, it's coming down. And the seasonality is also driven by nature. So when we put all of these things into picture, and then humans, we determine how much I need versus you need versus somebody needs, how much India needs versus the US needs. It's all determined based on many other factors, right? The demand side. So how do you quantify them? Are there tools? Are there data sets available? Can we come up with a good model to predict? That is the lifetime work for anybody. If you want to take, some of you might be already doing it anyway. I'm just saying. Again, understanding of these physical processes, right? The one that I showed as water cycle, which changes dynamically on a daily basis. Understanding of that is important to know exactly what is the occurrence and magnitude of precipitation, for instance, and how much of it is going to be available as water supplies. Right? So that's very, very interesting question to ask. Do I have enough supply? Do I have enough supply for meeting all my needs? If you ask that question going back to your place, start from there for understanding whether or not your basin is supplying water that you need, something like that. Excuse me. I showed this water cycle before. The reason I'm showing this again is, of course, there is an interesting article about this. I may share that later if I can. If not, you can also find out. Now, this water cycle is not holding good any longer. You know why? Any one single reason that why I say this water cycle is not holding good? Anybody? I need some volunteer to say something. Let it be wrong. Even if it's wrong, that's okay. But just tell me why this water cycle can be wrong or cannot be relied. Who is the reason? We, humans, right? We modified the system completely. So this drawing was drawn probably 100 years ago, talking about no humans on the planet. Water falls from the sky, evaporates, and then flows on the ground, gets into this system again, the water cycle that I showed before. But that's not the case anymore, right? When the rain falls, we stop it, we harvest it, right? Store it, use it, whatever reasons, and that is not accommodated in this graphics. And that is an interesting dimension to consider, right? Humans, we live on water, for water, with water, all kinds of things. We need to understand how much of our consumption is and how we can quantify those demands. That's one of the reasons I wanted to talk about hydrology. So now when we talk about hydrology, these are slow evolving fluxes on a daily to monthly to annual scales. But when it comes to floods, things are changing very quickly, right? So the foundation concept of hydrology, there are so many key elements that I wanted to show you here. That's why I underlined these terminologies. The occurrence and movement of water on and underground, the earth's surface, chemical and physical properties. It's not just the quantity side, right? We are talking about now quality. How good is the quality? Is that contaminated with E. coli? Or is that contaminated with nitrate and phosphorus? Arsenic, whatever pollution that we are having. So that chemical physical properties and water's relationship to biotic and abiotic environmental components, living and non-living systems. And then of course human effects on water. So this embodies the concept of hydrology. We are talking about the movement of water the quantity of water, good quality or bad quality kind of water, between humans and non-humans, living and non-living, connecting all of these dots is a very, very challenging process, right? So that's what hydrology is dealing with. So the discipline that we are in is one of the fantastic area to deal with, and you can make wonders, right? Hydrology has prominent land surface orientation because we talk about what's happening on the ground all the time. So that's why it's called land surface hydrologic cycle. The same way there is atmospheric hydrologic cycle or hydrologic budget, which is primarily driven by precipitation and all the other atmospheric processes. I think I mentioned this yesterday. We call precipitation as an input or the gain, variable. Atmospheric scientists call precipitation as a loss variable because they are losing that water. Then they talk about how the circulation happens, what is the humidity, wind speed, radiation, whatnot, all kinds of other atmospheric components. But when our life starts with when the drop of water falls on the ground. So we start talking about tracking them, quantifying them, timing them, and managing them, right? Disciplines, many disciplines are involved in this: biology, chemistry, ecology, mathematics, and physics. And of course, watershed is a small, kind of a basic unit or a small unit that we deal with, but it can be a river basin. There are terminologies that we use, basin, watershed, river, basins, to, sub basins, creeks. Even within those watersheds, we are having smaller creeks to bigger, streams to river. So there are a lot of terminologies and hydrology that we need to be relying on, relating to hydrology. But watershed is a very convenient unit because we delineate a watershed, we take account of how much water is falling within those delineated boundaries, and then we quantify how much is flowing downstream. And then tying that bottom portion of that watershed here with the measurement of gauges. We put some stream flow measurement device. We then say this amount of rainfall we got, this amount of runoff that we are getting. But there are so many other in-between processes that I showed before is happening in the water cycle. But the tying unit is the watershed response as stream flow in hydrology primarily. Climatology, of course, deals with applied science that examines fluxes of energy, mass, and momentum. There are three things that we see in the atmosphere. And also, of course, that is changing between land and ocean surfaces. What are these three things again? Energy, right? We talk about energy. How did we talk about energy yesterday? Radiation budget, for example. How much is the sun producing energy? How much is partitioned between latent heat flux, sensible heat flux, ground heat flux, right? That energy, right? And then mass. Now we are talking about the quantity in terms of depth units or volume units. 10 inches of rainfall or 200 cubic meters of water that flows in the river, something like that. That is the mass amount of water that when we talk about, that's also happening in the system. And then momentum. What's happening with momentum? When the mass is actually rolling over, it creates momentum, right? So river creates momentum, atmosphere creates momentum. So we want to understand the state of the climate with these three considerations: energy, mass, and momentum. All these climate models qualify or quantify these three variables for every grid, for every layer in the atmosphere to the land surface. These three primary elements. And again, this is not that simple. When we talk about wind coming from one grid to the next grid, and how much of a confusion it creates, to how much of moisture it brings, what is the momentum of that moisture that's coming from grid 1 to grid 2, right? This is quantified on a minute by minute basis, even in seconds, and then relaying that to the ground, of collecting all the data, assimilating all the data, and making decisions. In the video that I'm going to show you, you will realize that how important these variables are to be transferred on a timely, manner for making decisions on the ground. So we talk about vertical and horizontal fluxes of this energy, mass, and momentum, multiple layers, integrated system of land, ocean, and atmosphere in the climatology discipline. Seasonal variations are seen from atmospheric circulations, and I'll talk about atmospheric circulations later on this lecture. Again, atmospheric science phase of hydrologic cycle is climate-related phenomena that has seasonal variability. It's same as hydrology. We also have hydrologic cycle seasonal variability. Atmosphere also has the same thing. Okay, and the computational resource is important for modern climatology since simulation is involved. I kind of highlighted that, with showing the grids on a global scale and how to quantify those things. It's not easy to do manually, right? We need computational research. Supercomputers. Yesterday you were in the lab, supercomputing lab. Those are the places where they compile these models, run the models, get the outputs, and process them, making decisions. Again, some of these reports that we talk about, climate change synthesis, this is a little bit of a dated report, 2023. There is also a new one, I think, released even as of this month or last month with COP30 in Belém, Brazil. But message is the same. We talked up yesterday about you know, increasing trends or changing conditions. They are not totally changing too much from one report to the next report, but there may be some improvements with respect to predictions. Confidence levels have improved because of computational power. The processes defined within these computer models are really getting better day by day. We understand better with lots of data from both space, satellite data, and also on the ground. But now we talk about hydrology, climatology, but there is a new discipline called hydrometeorology, right? It is a very interesting discipline, but land atmospheric interaction comes in that place. But the traditional concept is about talking about the averages or mean or higher order moments. It could be standard deviation or variance, higher order statistics to express the atmospheric condition as the average temperature or average precipitation over a time, right? This is a very common thing in the traditional consideration. Climate, on the other hand, is expressed as the average of weather or the average state of the atmospheric conditions. So when I'm talking about weather for today, for Kozhikode, you can say temperature is 70 Fahrenheit or maybe 28, 30 degrees Celsius, let's say. That's weather. But you want to consider the month of December for Kozhikode and say the average temperature is around 25 or 30. That's climate system. Now we are talking about the long-term average of weather condition is related as climate. And these two distinctions are very important for us to understand what system are we talking about, hydroclimatology or hydrometeorology, right? With the systems, 5 systems that I talked about, spheres, we need to understand both hydrometeorology purpose of conditions of weather, and then we talk about climate. So energy, mass, and momentum. Now we are talking about multiple things, right? Scales, and then quantifying whether average or the state of the atmosphere at a given time frame. All of those things are really interesting, and that's what they do in hydrometeorology field. Okay. Again, I'm repeating this here. I don't need to belabor this point again. It's an interdisciplinary science, very interesting discipline, and we hydrologists can easily tack on or attach ourselves to that discipline very easily. Okay. Global hydrologic cycle is a unifying theme for hydroclimatology. The terrestrial branch of hydrologic cycle consists of inflow, outflow, and storage. Atmospheric branch also has the same precipitation, evaporation, and atmospheric transport of water. Like I said before, outflow of water from Earth is primarily through ET. 60 to 70% goes to the atmosphere, but precipitation is the atmospheric output is a gain for the terrestrial branch. So their loss is our gain, right? Atmospheric loss is the land surface people's gain. Again, I think I'm repeating here with respect to climate of the first kind and climate of the second kind, so I'm going to actually skip those. So let's actually now come to hydrologic extremes. 2 of those, today floods, tomorrow drought. Both are important. By seeing some of these topics today, you will think, I may be interested in looking at drought or floods, right? Floods today. Because it's going to be creating lots of interest in us to understand what's happening. Not just in our place, maybe around the world. Highly scopeful area of research. But then, when I'm talking about drought, you will think, oh wow, drought is also an important topic. So that's one of the reasons why we are going to emphasize on both floods and droughts little more extensively. But then we'll also talk about landslides, which is related to floods to some extent, because water is needed for landslides before it happens. So there is some connection to floods and landslides, so we will somehow highlight that. Why are we talking about floods and all these disasters now? Because it's happening a lot. Every place is expecting lots and lots of rain, right? Just these are the statistics, little bit of a dated one, but you now know why I'm showing the old ones, because you are seeing that more and more of the same thing. So 10 years ago, we talked about 40 million people were affected in South Asia. I'll show you some interesting maps there. And then that is not stopping, at that time. It's actually happening more and more of that. Caused primarily by climate variability. Now I'm introducing that term. And then climate change, population increase. People are moving in different places, settling down in different density, places. And then land use change and economic development is also causing significant problems. So this is another dated image that I show. The purpose is, this is West Africa, Bihar, North India area, Mumbai we see year after year, of course, Bihar floods. Country, of course, Kerala is also witnessing, but this is a little bit of a dated map, flood country or flood zone country. Around 75 lakh hectares of land affected for a given time period here. This is fixed, but this is changing year after year after year. The infrastructure damage that we are seeing is exponentially increasing in India and everywhere else. So we want to know what is the flood inundation depth for a given location, right? Ultimately. And how often we are going to get that floods, right? How deep is the water? How much in advance we can understand that we are going to have floods, and whether or not we have the resources to communicate them, and then whether or not we can move to higher grounds with timely warnings. All of those things matter, but fundamentally, understanding the occurrence and movement of water in hydrology that I talked about before is very important. So how much is the rainfall that we get? And quantifying that is the first step, right? So before even we go in depth. So I think I showed you this slide yesterday, so I'm going to skip. Bangladesh, India, Nepal, all these places are heavily affected by floods and heavy monsoon rain year after year after year. I mean, 2015 was the year that I was personally witnessing when I was in Chennai, en route from Singapore to US, and I was going, I could not come to Chennai airport. Then I directly went to New Delhi and then left from there. That was 2015. I thought people are coming up to terms with understanding that, wow, we now know how to quantify drought or floods and then see whether or not we can be ready for the next one. No, 2017 came, 2020, 21, 24, now 25. As of this morning, we are seeing lots of flooded areas impacted in Sri Lanka, Indonesia, South India, right? Ditwa is the storm that we are talking about. So many, many times we are seeing this over and over and over. What are we doing about it? To do something, you have to understand the system, right? If you want to manage a system, what do you need to do? You have to understand it first. To quantify systems and see then whether or not we can manage is the approach to take, right? So floods are one of the major disasters, including droughts also. They are causing more deaths. Extreme events are caused by increased atmospheric moisture. We talked about that, relationship of holding moisture up to 7% more for every degree increase in temperature, because the atmosphere can hold more moisture, right? And they are coming down as heavy rainfall. So varieties of rainfall, I don't want to go into the depth about precipitation process, how the rainfall occurs, whether it's convective, like evaporation based, coming down as rainfall again, thunderstorms, or orographic, the flow from the sea breeze lifted up into the atmosphere because of the mountains and then coming down as rainfall, or through the monsoonal cycles, that's what we have, different types of storms, and they bring different types of rainfall quantities. That's very important. You can read them through on your own, but what we are talking about is, of course, increased atmospheric moisture, shifting circulation, and increased ET. In some places, we are seeing more vegetation. India is greening up, including western, Rajasthan area, or maybe central India and northern India. We are talking about more greening. That means more pumping of water into the atmosphere. Shifting circulations. Jet streams are happening all the time from west to east at the level of 11 kilometers or 12 kilometers. You see them, but those jet streams can move up or down, bringing moisture, sucking moisture from the ocean and creating different types of dynamics, right? When we talk about floods, we are not just confining to this time period. It started back in, civilization, Harappa, Mohenjo-daro to Egyptian civilization. If you're talking about Persian civilization, they have come up with water management strategies, right, from extreme events. And then particularly acute in regions on stream flow for irrigation. Extreme events are going to be really driving the process of irrigation, water supplies for urban and industrial areas, flood protection, hydropower protection, or generation. Again, understanding the relationship between these anomalous meteorological, climatological, hydrological event is the first step, developing strategies to address these extreme events. Now I'm going to actually introduce the terminologies to bring everybody up to speed. Some of you are good hydrodynamic, having background on hydrodynamics. Some are probably seeing this for the first time, right? So let's actually break it down into some simple terms here. When we see the water flowing into in the graphic that I'm showing here, you see it's confined as a river, right? It's within the banks, but then it swells, it flows over, right? So we call this as floodplains. So the river, the valley, the contributing area that we are talking about. So we are not just worried about the quantity of water that's flowing within the system. We are talking about how much is actually it's going to go over bank or breach, and how much is the inundation area beyond the stream segments that we are interested in. So HECRAS type of models do that flood inundation mapping, 1D, 2D, variety of models. Of course, hydrology is important, and then we route the flow through hydrodynamics or hydraulics model to quantify, right? So these floodplains are changing. The takeaway, you can read this later, but the takeaway here is the floodplain topography is changing, channels are changing the direction, geomorphology changes, and we are also building houses right in these areas, right close to these banks. So we are putting pressure on the system, and we have population increase, right? Increased population, urbanization creates people go closer to the water, and putting themselves in the path of risk. So again, river is confined and tamed or maintained within this channel if everything goes normal. But normally that does not happen, right? So when there is more flow, it goes all the way up to the bank. So they call bank full width or bank full flow. And then hydrologic floodplain is all the way, before we enter into the natural landscape, we are talking about the floodplains here. So in another graphic also I showed this. And then this is the elevation that we are talking about in a ravine or in a valley. So we are looking at topographic floodplain, hydrologic floodplain, bank full of water, and then bank full depth that we have. So quantifying all of these things, of course, require good amount of data, good understanding of the processes, and then connecting all these dots, quantification of flow from upstream in the catchments into the channel and into the downstream, into the outlets. Again, I'll skip this. I mean, these are big river systems, huge river systems. Ganges, that one that we have here, is about 75,000 cubic meters per second of peak discharge. It's a huge quantity that we are talking about. Brahmaputra, for example, in India, is 81,000 cubic meters per second. These are huge river systems. When they show the signs of stress because of heavy monsoon flows, building anything to protect from these floods is going to be really a challenge, right? So just imagine the quantity. That's very important. I mean, we get moved away when we look at the water that's flowing in the river. But we need to understand how to control the damage. Of course, there are people building dams, levees, bypass channels, land use control on the floodplains, like, they put wetlands, restore wetlands, barrier islands they put here, dikes. I don't know if you remember, some of you might be young at that time. 2005, we had New Orleans. There was a huge flood, hurricane, I think Katrina, I think, if I remember correct. So hurricane came and went after a day, but the rain started soaking in from the neighboring areas. The dikes started failing, and the disaster happened after the rain stopped, and the whole city was underwater. Lots of people died. You can Google and see, Hurricane Katrina and its effect in 2005. It's a huge, life-changing event for many people in Louisiana. But it didn't stop. Even in 2017, Hurricane Harvey hit Houston, inundating the whole area. And every place like that, Mumbai floods year after year, you see in June, right? June, July, August, around. Hyderabad is getting flooded. Bangalore is getting flooded. Chennai is getting flooded. Gurgaon is getting flooded. So no place is spared from these disasters. How do we control the flow is depending on the type of resource that we have and the necessity and what kind of protection that you need to have. We talked about risk yesterday a little bit, right? So when we talk about risk, it's very important what kind of risk we have, 100-year flood or 500-year flood that we are getting every day now, or what kind of budget we have to really build structure. If we want to build a dam, it's going to cost crores and crores of rupees, right? And also it's going to have environmental degradation issues. So you have to compromise on so many things and quantify what is the best approach to do. So for flood control, again, floods are mostly aligned with hydrometeorology than hydroclimatology, right? And then hydroclimatology relates with the hydrometeorological scale, atmospheric activity. Basically, hydroclimatology is also important, but on the atmospheric side, they talk about what are the drivers that bring the moisture into the region. And then when it comes, what happens on the ground on a broader time step also, but then on a local scale. Floods are happening at a local scale. So any model that we develop should be able to capture the local, topography conditions and see how much of a depth, inundation depth that we create. So a combination of that plus circulation patterns will help us understand what kind of drought or floods we are talking about here, right? So I think this I talked about already in terms of convective storms, types of rainfall events that we bring, and then snow melt. In the US and higher latitude regions, it's also, in addition to liquid rainfall, we have snow that is accumulating between, let's say, November, around this time, to March. And when this temperature goes up from April, May, all this snow starts melting, and then that creates flooding. So that's called snow melt driven flooding, which is not common here, but maybe in Jammu Kashmir and other regions in the north, you have some of those issues. Again, for floods, you have to understand the antecedent conditions. What is the condition that we have? In the video that I'm going to show you, you will see what they talk about. First wave of rain brings moisture, right? Supplies moisture to the ground, saturates the ground, and then there is another wave of rainfall. When it comes, it starts flowing over the ground, creating flash floods primarily. Again, availability of moisture and atmospheric conditions are very, very important. I'm going to actually skip some of these things in the interest of time, because these are basic stuff I already talked about. For example, floods from the atmospheric side is driven by precipitation, right? But on the land side, watershed characteristics are very, very important. The time it takes for the water droplet to move within the system on the ground, and of course, the lag that we have between the amount of rainfall falls on the ground to amount of runoff that shows up the downstream. There is some kind of a lag or a temporal decoupling that's happening. So we need to understand, depending on the location, that changes. Mountainous terrain like here, instantaneously it shows up when the rain happens in the higher elevations. But in other places, if it's relatively flat, it may take days before it shows up, right? Again, when we talk about floods, we need to understand the magnitude or the volume, and then the duration, how long is the rainfall event that we talk about, and then frequency, how often we have this kind of event. So intensity or magnitude, duration, and frequency are really three terms that we want to capture or capitalize on when we quantify drought. So, or I'm sorry, again, floods. Knowledge of these is necessary for engineering design, economic and floodplain management, and decision making. So, all of these, major things are very important. I think yesterday we touched a little bit in the statistics class, basics. These are the terms people use in flood modeling: return periods, exceedance probability, right? When we talk about 1% flood, that's basically 1 over T, that is 100-year floods. Basically, probability is 1 over the time, and 1% flood or 0.01 means it's 100-year flood. You will hear this terminology, right? Oh, we saw a 100-year flood in Chennai or 500-year flood. So that means what? We are talking about this kind of events happening once in every 100 years, right? Typically. But it does not have that clock. The rain does not have that clock to come exactly every 100 years. It's now coming more often. Every 100-year floods are coming every 5 years nowadays. 500-year floods are coming every 20 years now. So the intensity of these storms that are bringing and changing the way how we are quantifying these or defining these design storms or design periods for floods. Typically, engineers use this, right? 100-year floods are used for designing drainage structures, culverts, bridges. 500-year floods are used for designing dams, spillways, whatnot. And depending on the budget, like I said, and then the quantity of risk that we have to face is going to help us. If the place is going to be vulnerable for 500-year floods, there is no matter how much money you spend, you have to spend that amount to really make sure that that place is safe. So people use this metrics in our field. Flash floods is another important thing, and you will see in that video also flash floods. So that does not give enough time. A combination of meteorological factors and landscape conditions create a large area flooding in a rapid fashion. Mesoscale convective systems, the atmospheric circulation, that is the primary driver. And when the precipitation producing atmospheric conditions are organized into multicellular convective systems, they gradually move. Similar to what we are seeing with monsoon system, right? It sets up in June from the coast of Kerala. It moves in, right? It's kind of a squall line, but they are not really squall. Squall lines are used in the meteorological literature in a very shorter time scale. But we are talking about monsoon movement is basically a seasonal cycle, but still they are all big. The system like this, of this scale, this is central US, so they kind of show the movement of the line of storms that crosses the area. You will see that in the video also, I'll show you again. Most of the floods are produced by quasi-stationary mesocycle convective systems. What do I mean by that? Quasi-stationary. They move, I said they move because of the rotation Coriolis effect of the earth, but they don't move that fast sometimes. They move, stop sometimes and then dump the rainfall, move slowly. It happens even with Ditwa. I think they talked about slow moving system. And when that happens, you are really seeing that flood producing event. And again, that is important to understand how fast the system moves, how much of a rain it will bring before even we start thinking about how to model floods, right? And these are the topics again I think I covered. Again, the onset of floods. There is an interesting video I normally show, but we don't have time for that, for flash floods. But I want to stop here. This is 10:16, 1 hour after. But should we stop here or continue? Okay. So how much time that we take for the break now? 5 minutes? 10 minutes? Okay. So let's reassemble again with starting with the video, and I will show you 3 cities where the floods happened. But then some of the concepts that we haven't covered, we will come back after finishing first few minutes of watching that video. Thank you. Is the audio in the background okay?
September 2024. Torrential rain hits North Carolina, triggering flash floods that surge down valleys and destroy buildings.
It just ripped it in half.
Nobody in this part of the country has ever seen anything like this before. It was devastating.
1 month later, in Spain, a massive flood hits Valencia.
Everything was flooded with 3 feet of water, which was pushing cars down the streets, into buildings.
Madre mia! The flood kills more than 200 people.
Something went wrong in this flood. We know that the flood forecasting and warning system didn't work as it should have done.
Then, in central Texas, on the 4th of July, 2025, deadly floods kill over 130 people. Are flash floods becoming more frequent and more devastating?
There was a cascading and compounding effect of this storm, which I fear is a harbinger of things to come.
What can we do to protect ourselves from these deadly inundations? Super floods. Right now on Nova.
As an American-based supplier to the construction industry, Carlisle is committed to developing a diverse workplace that supports our employees' advancement into the next generation of leaders, from the manufacturing floor to the front office. Learn more at carlisle.com.
On the 4th of July, 2025, an intense thunderstorm in central Texas generates floods that kill more than 130 people, including at least 39 children. It's the deadliest inland flooding in the United States in nearly half a century. But this shocking disaster isn't an isolated event. In the preceding 12 months, 2 other record-breaking storms also produced devastating floods. One in North Carolina, the other in Europe. Altogether, the 3 storms leave over 450 people dead. What can we learn from these disasters to better protect us in the future? Asheville, North Carolina. It's a popular tourist destination. Around 14 million people visit the city every year to enjoy its vibrant arts and culture, historic buildings, and spectacular mountain scenery. Asheville's location, over 250 miles from the coast and 2,000 feet up in the Blue Ridge Mountains, puts it far from the storm surges of Atlantic hurricanes, which made many people think it was relatively safe from extreme weather. But that all changed in the autumn of 2024. Wednesday, September 25th. Torrential rain pummels North Carolina, and it looks like it's about to get worse. For 8 days, meteorologists have been monitoring a weather system coming in from the Gulf.
By midday Monday, we had what we call potential tropical cyclone. Nothing has actually formed, but something is going to form. And already then we were talking about significant heavy rainfall.
By Wednesday morning, the tropical cyclone has been named Helene and grown into a hurricane. Its predicted track puts it on a course toward western North Carolina and Asheville. The city sits at the junction of two rivers, the French Broad and the Swannanoa. On Wednesday afternoon, the National Weather Service issues a worrying forecast.
We had a river forecast, and our hydrologist put in there the potential for ruinous flooding along the French Broad and Swannanoa rivers. He put in there, this has the potential to be once in a lifetime flooding. Consider relocating if you live along the French Broad and Swannanoa rivers. We were very concerned and, quite frankly, getting very scared at that point.
But the trouble starts even before Hurricane Helene reaches North Carolina. On Thursday afternoon, the eye of Helene is still 500 miles away in the Gulf. But in Asheville, after 2 days of heavy rain, the French Broad River is already beginning to flood. That night, at 10 past 11, Helene makes landfall on the Florida coast as a Category 4 storm. Through the night, it tracks north, and in the early hours of Friday morning, dumps more rain onto Asheville and the surrounding mountains. 8 miles east of Asheville lies the town of Swannanoa, named after the river that flows through it. On Friday morning, the overnight rain from Helene swells the river, and it rises rapidly. Michael Bergen is at home with his partner, an 18-year-old son, when water starts flooding their street.
It was around 7:30 in the morning. I did get an alert on my phone saying to evacuate. At that time, the water was about halfway up our cars outside, so evacuating didn't seem possible. Our idea was to go up to the attic first.
But the water continues to rise.
We were up in the attic for a while. The water started sloshing into the attic a little bit, and we didn't want to get trapped, so we decided to swim down into our kitchen.
With water nearly up to the ceiling, they try to escape through the windows.
We were going up and getting air and then swimming down and trying to get the windows open, and neither one of them would budge. And then eventually my son was able to break the window open. We swam through the window and then got up on our roof.
14 miles downstream, the floodwater flowing down the Swannanoa reaches Asheville.
I was on a corner unit that basically looked right up the river. Early afternoon, mid-afternoon is when it started rising a lot faster. When it started to flood first floor apartments, everybody on the second floor was like, oh man, like that's crazy. And then it hit the second floor. Oh my God. It kept coming and kept coming. At first it was just random debris, you know, litter, trash, or some tires, street signs. By 1 o'clock or so, we started to see box trucks and shipping containers and really quite large stuff. We could see these things coming a ways away, and it just felt like slow motion. It literally folded a giant shipping container like tinfoil. It just wrapped around it. Unbelievable. It's pretty terrifying because everything looked like it was going to hit us. And then kind of last minute, it would whoosh its way out into the river.
Oh, come on, baby. Miss us.
Certainly the scariest one was seeing entire buildings coming down the river.
This isn't just a roof. This is the entire Asheville Tea Company building.
Holy. It just ripped it in half.
Upstream in Swannanoa, floodwater continues to pour through Michael's neighborhood.
We were on the roof for a total of about 3 hours. We started hearing foundations cracking. It was very surreal and very scary.
Eventually, neighbors and kayaks carry Michael and his family to safety. In the mid-afternoon, the flood reaches its peak. All along the Swannanoa River, it has devastated communities. On the morning of Saturday, September 28th, the people of western North Carolina wake up to scenes of devastation.
It looked like a bomb had gone off. I mean, the destruction is incredible. Overturned cars stacked on top of each other. Incredible depth of just mud that you had to kind of really work your way to get through. Streets that were just ripped up. It completely changed the landscape.
On Michael Street, everything is filled with mud.
The water went down remarkably fast. Most things were destroyed, obviously. It just was really upsetting.
I will stop here and come back to showing this again a little bit later. I mean, this is the same scenario, but different place in Valencia, Spain, and then in another place in the U.S., Texas, we saw happening. Yeah, I can stand here and talk. Most important thing, we need to understand the drivers. What causes these floods? That will be more scientific for us to understand. But you want to first understand why. I mean, the extent and the damage that what we see. It's pretty typical that what we are seeing in India to some extent. Why not? For example, that Kerala saw is similar to this. Starting from some mountainous upstream watershed, bringing lots of water and mud. And Chamoli in Uttarakhand, for example, the landslide that happened, floods that happened there, Himachal Pradesh or Jammu Kashmir, all of these places are seeing similar kinds of extreme events, but the settings are different. So they talk about it. I will introduce the terms circulation, high pressure, low pressure, troughs, and all that. They call cutoff trough. Basically, that creates this whole thing, the atmospheric process. You will understand it better when, after I introduce some theory part of that circulation, in this next few minutes. Then we will come back to this. It may not be possible to cover everything today, but I will show in bits and pieces so you will understand. The ending message is very loud and clear and very important for us to take away. They are saying technology, how to communicate, how to disseminate the warning systems, what failed, what should be done, all kinds of discussions. That's very useful. I mean, you are all young, you are going to be the future, flood modelers and drought modelers. You want to understand what kind of things are happening around. So that will give you and inform you and equip you. So that's the intent for me during this class. Okay, I'm going to see the slides here. Okay. Yeah, so let's actually talk about the watershed. The main idea here is, of course, as I said before, for hydrologists, watershed is a unit that we operate under, which actually converts rainfall into runoff. So partitioning of rainfall into runoff is the part that we need to understand, but there are a lot of smaller details when we talk about watershed. In this case, as you can see here, I think I better use this one. Need some help here. So, looking at this graphics, you can see watershed being developed with urban areas, agriculture, forests are removed, downstream, development. Of course, we are calling this as a watershed. It's not a natural watershed, developed watershed. It's not pristine, but there are many watersheds in the world and including in India are pristine. But to transform the partitioning of rainfall into runoff, we need to understand every region, every location precisely. There are physiographic factors, the shape of the watershed, size, slope, orientation, land cover, land use, surface infiltration, soil types, and then stream channel network for a given watershed, size, shape, roughness, and length. I think maybe some screen resolution issue here. I think I'm going to live with that. So let's look at, I'm showing a old graphic here. This is how in the 60s and 70s when they built models, they came up with boxes of different components, coded them in computer programs, and then run them. This is a model, right? But precipitation, as you know, is the most important thing, and it's a bulk transfer process, meaning both it brings a heavy amount of rainfall, unlike molecular or diffusion process for evaporation. Evaporation is like water vapor moving in, but this one is bulk transfer with water droplets. When they cannot hold up in the atmosphere because of gravity, they fall, right? So that is the opposite of evaporation. The amount, intensity, space, and time are really important, and presence of vegetation on the ground that absorbs the impact of raindrops and reduces soil erosion. So, probable maximum precipitation is the term WMO introduced, and that's widely used. It's a theoretically the greatest amount of precipitation depth for a given storm. They divide the country with contours showing what is the PMP for a given location. 20 inches, 30 inches, 40 inches, something like that. And design people use those numbers for calculating their infrastructure, whether it is storm sewers, culverts, drainage network, or even bridges and waterways. Um, Basically, National Weather Service in the US combines physical and statistical analysis to quantify the storm system and the movement of rainfall, precipitation maximum or probable maximum precipitation. But main thing is this, partitioning of precipitation happens in many levels, right? So when it falls on the ground, of course, there are vegetation, and then the stem flow through the plants and through the canopy, and how it reaches the ground is ultimately that we are interested in looking at. So this is at the canopy level or tree level, right, individually. So when we talk about precipitation, what kind of terminologies we are using here? If you notice here, amount of precipitation, how much is actually getting lost, what is the amount of interception that we have, what is the through flow, meaning through the stems and stem flow also, and then interception and infiltration. You saw that in another NASA graphics that I was showing before. Modeling this at a tree level, and think about expanding this at the watershed scale or even at the country scale, it's a humongous process, right? So you need to define these parameters. You need to define the right inputs, precipitation, for example, in this case. If you don't do that, then the partitioning will not be meaningful. It may not be accurately predicting what is the amount of water that goes up as ET and how much is the amount of water goes into the soil and how much is available for runoff. So every term is important in water budget for hydrologists. Interception is one thing. I'm just introducing the terms. We'll not get into the details here. The plant leaf, depending on the type of leaves, narrow needle leaf versus broad leafed, seasonal versus perennial, deciduous forests, all kinds of vegetative species intercept differently. But for flood forecasting, this interception amount of rainfall is needed, but again depends on the location. Varies with the type of leaf size, shape, and leaf density. rain intensity, duration, and wind are the meteorological drivers for this interception. Daytime or nighttime precipitation also amount of rainfall that is intercepted is impacted because of the time. When the daytime rainfall happens, part of it is intercepted and goes back to the atmosphere as evaporation, direct evaporation. But if it happens in the nighttime, it stays on the leaf, it falls onto the ground, it adds to the soil moisture. These are smaller quantities, but over a large area, if you look at, they become really big, and the quantification of runoff becomes inaccurate if you don't consider all of them. Okay. Water holding capacity of the surface is limited again. They don't hold too much, but over an area, if you look at, the amount of interception can be a big amount. Again, the storage capacity is expressed in terms of equivalent depth per ground area. The range is somewhere between 1 and 6 in the US for coniferous forests. It can change from place to place, but this is a number that people should consider when we are talking about storms of moderate amount of rainfall that brings to quantify the right amount of runoff. So vegetation matters in the interception. So interception storage, again, I will skip all this for now. So the interception part is one quantity, and then through fall and stem flow, like I said before, is the amount of rain that reaches the ground directly through the vegetation canopy or as drip from leaves, twigs, and stems. Again, intercepted rain moving down the twigs and stems of the plants, when the interception storage exceeds its capacity. When the leaf cannot hold anymore, then the amount of water that's actually intercepted through the stems and twigs flows into the ground. Okay, it's a function of the size of the bark of the plant or the tree. Substantial amount of moisture is sent to the base, leading to higher infiltration rate. So when the infiltration rate is higher, the soil can hold only so much of moisture, right? So if the plants can directly send them and recharge the soil column and quickly saturating, that's a nice ingredient for setting the runoff flood event. So as you can see here from this graphic, of course, intercepted amount of rainfall through flow, and then part of it is going on the ground as surface runoff, part of it is going as through flow underground, and some of it is going into the groundwater, which will not show up for flood forecasting, but it can be important for landslides. We'll talk about that later. So I think I'm covering this, but the one thing that you want to remember is the capillary forces and gravity, the soil column. Depending on the soil type, sand, clay versus silt, they behave differently. Their fill capacity is different. Their water holding capacity, which is a function of the difference between fill capacity and wilting point, that's different. If they cannot hold that excess moisture, of course, it has to either drain or it has to flow on the ground. Right? It again depends on the topography. So depression storage is a factor for flood forecasting, flood modeling. When precipitation exceeds infiltration rate, so when it starts raining, it slowly, reaching the capacity of the soil saturation. But that is the infiltration rate is a function of the soil type. If precipitation is higher than infiltration rate, no problem. It will keep on, accumulating that on the surface as ponding. And then retention of that water in micro depression constitutes depression storage. Over a large area, it can be a big amount, 3 to 13 millimeters. Evaporation and infiltration also empty. Directly water evaporates from this depression storage. But if you have lot of potholes or areas that can hold water, that is good in a way because it does not create peak flows right away. And this is called common slang is called monkey cheek approach. What it means is those days, our early, kings and the people who ruled, in other parts of the world also, including Thailand, that I remember, it's like a monkey. When it eats, it'll actually store some of it and then eats very slowly later, right? That the same thing applies here for rainfall interception. It stores immediately onto this depression storage. It does not enhance the peak runoff, but after that depression storage is getting filled, it starts flowing. That's the monkey cheek approach. And then soil moisture is a very important variable for calculating runoff. Greatest proportion infiltrates into the soil. For some conditions, don't, I'll not go into the detail. Infiltration itself is a big topic, and soil moisture itself is a big topic. And the models have all these algorithms defined, so we don't need to worry about them. On the last day, I think we will talk about HMS, where you are going to see some of these terminologies used in the model, and model estimates these quantities. But there are methodologies. For example, infiltration is by green amped or SWOT model. If somebody is using, you will see green amped versus Horton's equation, and different types of infiltration. Same way with soil moisture. How much is the moisture that's available in the root zone? That's very important, especially both for drought and floods. The amount of water that the root zone can hold is very, very important to understand. Field capacity and wilting point are the two terminologies, again, people use to define the upper level for field capacity and the lower level for wilting point. The water that's available between field capacity and wilting point is taken by the plants. If the water drops below that, the amount of moisture that's dropping below that available water holding capacity, plants will die. And that's when they recharge. But when they are excess, they are going to flow on the surface as runoff. Okay? Again, it's very critical for runoff, so contributes to the partitioning of precipitation to ET by serving as storage. So soil evaporation decreases once few millimeters of soil have dried. So when in the beginning of any event, rainfall event, of course, you have surface soil moisture that's readily transported back to the atmosphere as water vapor. But places like India, that's very common. On a hot summer day, convective rainfall is created based on the evaporation that we have. But again, for runoff calculations, if you take that moisture out of the picture, then you are able to come up with the right quantity of runoff. Water in the top few tens of centimeters of soil is available for plants, like I said before. And then overland flow, right? It happens when the soil is saturated and when the water that is actually exceeds the depression storage, it starts flowing, right? And then it depends on infiltration, rainfall rate, infiltration rate, land surface slope, and then obstructions to water movement. And again, it's the initiation of the runoff. In the urban areas, for example, you see flash floods are the waves that we are talking about. Sorry, the waves that we are looking at here, it's part of the overland flow dynamics, and particularly the velocity and the depth part simulated by Heck-RAS kind of models are very important. How fast the wave front moves. Again, it depends on the terrain, it depends on the condition, whether it's natural versus asphalt or built up area, right? Again, I think I talked about through flows, and groundwater is the last one. It recharges into the groundwater, which is not available for runoff. So again, for geologists, probably this is an important part to understand, like how much of water that's going into the groundwater, whether or not it's depleting the aquifer or adding recharge into the groundwater for long-term water management plans. But for floods, I don't think we need to be worrying too much about groundwater storage in this case. But essentially, we need to understand whether we are living or the watershed is a confined aquifer or unconfined aquifer, whether or not the water will go into the system before it starts flowing. Those general understanding is needed for flood modeling. And again, when you look at this is again for groundwater class that we use, there is a hard layer, clay layer or rock, whatever we call, and they are called again the subsurface hard, hard to permeate or infiltrate, where we take water directly by pumping in. This is called confined aquifer. There is a limited amount of water, but of course the recharge area is here. If water enters into the system, water accumulates into the groundwater over hundreds of years, right? But we are depleting them at a faster rate. This comes under water management topic, but I just wanted to introduce this. Unconfined aquifer is the one above this hard layer from the surface. This is the confined aquifer, and the amount of water is depending on the specific yield or the water that's available in the aquifer that is stored over millions of years basically. But we are depleting in many parts of India, and also in the US. I see a lot of places that are getting stressed because of over pumping of groundwater and free electricity that's being available for people to pump as much as possible, without realizing that if the discharge is not in balance with recharge, then we are talking about depletion of this water table, and that's becoming unsustainable for many parts of India. And that's a big problem for water management as well. But now coming to hydrograph, again, there are some hydrologists here who might have a good understanding of this graph, but we need to understand, to really draw basic understanding about flood hydrology. Okay, so for a given time, we put the quantity Q, amount of water in cubic meters per second, flow rate, right? That is measured in the river by measuring the river stages and converting the river stage into discharge is another topic. We are not talking about that. But let's say we are converting the stage into discharge using some conversion, and then this discharge is showing up here for a given storm. Right? This is the starting point or the rising limb, and this is the falling limb. And the baseline is basically between the lowest portion to the lowest portion of the storm that we are talking about. So if the storm duration is, let's say, 15 minutes or 1 hour or 2 hours, the runoff hydrograph can be having a lag. You remember I talked about the lag in the morning. So the decoupling of that rainfall duration, it's not exactly, when the rain comes, you will see runoff in the river immediately. It is not like that. There is a non-linear process, and that process takes depending on the condition of the watershed. So now this is the crest, this is the peak amount of water that we are talking about. So this magnitude is the one that we should be worried about. When we talk about floods, that is the peak flow that we always think about. So here, rainfall, or they call net rainfall. What is net rainfall? We talk about the losses, right? What are the losses? Evaporation, infiltration, percolation into the groundwater, all of those terminologies are taken out from the precipitation. Then anything that's available for runoff, that's the amount called net rainfall. The volume of direct runoff that we say DRO is basically converting this depth into this volume. That's what we are doing. So area under this graph is the volume, but each of these ordinates will have flow rates, right? Flow rate at 1 o'clock, 2 o'clock, 3 o'clock. The peak flow can happen at the 5 o'clock or 5th hour, something like that, if it's a 9-hour storm. So what I'm talking about here is the basic hydrograph, recession part here, the point of inflection where we draw the base flow. Base flow is the amount of water that flows in the river round the year with or without storms, okay, fed by the groundwater system or some other means. But that amount of water should be also included when we are talking about the flood flows. But we in case of the conversion of this rainfall into runoff, this peak flow and the timing of that peak is very, very important. One other big important point that we need to remember when we talk about hydrograph is the urbanization part, right? So I just wanted to show you here. I'm not sure if you can see from the back. I'll try my best to show. So I draw this hydrograph here, right? So this is the general hydrograph like that one. So the peak volume is very important, and the timing to the peak time is very important, right? This is Q peak. We want to measure this. In the river systems that we saw in the video, the peak flow is the quantity they measure and then relay that information to the people on the ground to tell that there is going to be flooding and things like that. So this is Q here, cubic meters per second, okay? And So this amount of water is your water that is produced by the rainfall directly, storm hydrograph, that's what we say, right? But this is a kind of watershed that I showed theoretically, right? For a watershed that is modestly developed with some urban areas, some forest, agriculture, all kinds of mixed land uses. But in today's world, what are we doing to these landscapes? We are converting them from natural system to a man-made system, engineered watershed with lot of roads, lot of pavements, lot of buildings, right? Converting permeable area into impermeable areas. So in that scenario, what happens to floods? What happens to these peak flows? What happens to the time? That is the thinking that we should have. Anybody can volunteer here. The question that I'm asking here is, when the watershed is developed, what happens to this peak flow? Okay. And then I cannot hear, I'm sorry. Can you be louder? On this side, I heard somebody saying something. I cannot hear. Time to peak will reduce. That's what the other answer was. Priyank, right? Priyank was saying that. So what other thing that we should remember is that the shift in the hydrograph and then the quantity also changes. The shifting of time is one thing, right? And then we are talking about this changed amount of water that's happening. This is the peak flow now, right? We are talking about peak flow that's also happening. Instead of, let's say, 5 hours, now it's happening in 2 hours, let's say. 5 hour versus 2 hour. So the conversion of watersheds, the land cover change that we are introducing into the watershed is creating this shift, natural hydrograph to an artificial hydrograph with increased peak and earlier time to reach that peak. That means it's faster response. The outlet that what we are seeing as the flow that we measure and quantify, right, is happening quickly, and people need to know that, and that information needs to be shared in flood modeling work. This is the crux of the point that we want to be highlighting. As hydrologists, when you try to model, what kind of shift are we talking about? What kind of storm system that what we are talking about? Whether it's a uniform rainfall or a front-loaded storm system or a, you know, tail-loaded water storm system or something like that. Uniform versus front versus moisture, depending on the way how moisture is brought into the watershed. So we need to quantify this amount, right? So that's the idea, and models are there to do that. I think we are about time here, so I'm going to actually skip some of those things, and let's actually go to the last part of this lecture, and then I'll show a little bit about the video. Is the next speaker here already? Not yet, so that's good news because we can play the video a little bit. I want to actually, we talked about hydrometeorology, hydroclimatology, right? These are all mostly on the land surface, but I also talked a little bit about the drivers. And the video also talked a little bit about how the hurricanes from Gulf of Mexico moved in, right? So in Indian context, I want to introduce you to the circulation patterns in on a seasonal scale. There are 3 or 4 of them that I want you to be aware of. I'm going to actually skip all this. These are atmospheric circulation that we already talked about. So now this is a summertime situation. This is winter time for India. I mentioned several times this morning about the jet streams, right? It's actually flowing right above us all the time around the year. Depending on where you are, whether it's right above us or right in front of us or right behind us, we don't know. But let's say Kerala is here. So typical summertime, the jet stream is intertropical convergence zone, ITCZ, they call low pressure system. So it goes to the north, bringing the inblowing winds crossing a warm, moist sea. So this is the setting for us to bring the moisture for Kerala coast, southwest monsoon, right, in the summertime. What happens in the winter? The cold air mass coming, high pressure builds in here, and the low pressure jet is moving downstream, downside. So that's why around this time, of course, we call this as cold, relatively colder than summertime in India. Of course, if it happens in Arctic and Antarctic, of course, we see freezing conditions. Today in my hometown, it is snowing. So it's because the Arctic air mass. I'll show that graphics later. But the idea between these jet streams going back and forth is the driver, fundamental part of atmospheric circulation that we need to be understanding. Okay, so now we also have to think about a couple more oscillations that are relevant to Indian context. One is called Madden-Julian oscillation. Okay, so keep in mind about that general ITCZ low pressure jet streams flowing in the summer versus winter for India. Okay, that is one thing. And now MJOs, when we talk about, this is the unusual warming of the ocean right below us. This is India. You cannot see clearly. I think I may have a blown up picture. Let me see if I have that. Yeah, so maybe this one might be better. So India is here. So these warmer conditions eastward, it actually flows near the equator towards Indonesia, for example. But when the warm water here in the Indian Ocean, Arabian Sea, Indian Ocean is happening, of course, it creates this convective activity. It's basically counterclockwise on a planetary scale rotation. It happens in every season basically, and it brings the moisture. So think about the jet stream that I said before, summertime jet stream, and then this circulation. So what happens is that when the jet stream moves up and it takes the circulation, ocean circulation that brings water vapor from ocean to the land, and added to that jet stream, it brings moisture to the Kerala coast. That is the onset of monsoon season, right? It actually, MJO has got positive phase and negative phase. When the temperature is warmer than usual, that's warm phase. When the temperature is colder than usual, it's cold phase. Warm phase brings more rainfall, monsoon rainfall for India compared to the cold phase. Okay, and then of course, these indices are calculated for the whole globe. For the Indian context, for Indian Ocean, close to the Indian boundaries, if you pick the data that's available and then look at what are the settings that we have for a given season. Are we going to have record setting rainfall events or not is kind of the index that you need to remember, MJO. The other one I talked about is ENSO, El Nino Southern Oscillation. I'm showing the example of the Pacific coast of the US. This is Pacific, West Coast. California is here, Washington, Seattle is here. High pressure is building up. There is a storm activity going on in the equatorial region, okay? And when in the 10 days before, they can actually look at this in the forecast. In the climate forecast, seasonal forecast, they are able to come up with understanding what's happening to this jet stream. Again, similar to Indian jet stream that I'm talking about, this jet stream that's actually going this way, right? And now when the closer to the 3 to 5 day before the heavy rainfall event, since the high pressure is going up north and this is moving to the west coast, this is bringing heavy rainfall right around the coastal regions of the west coast. So this happens probably in a span of 10 days. People can predict. They'll say there is some unusual warming, El Nino Southern Oscillation that's happening in the Pacific 10 days before, and if they see high pressure setting up on the coastal part of the landmass, then they say how that moisture is going to be moving. That is for the US conditions. And again, it also has ramifications for India. El Nino means it's a warm phase. There is another thing that we need to understand. One second, I may have that. Yeah. So here, the temperature, sea surface temperature, this is again, I'm sorry, I did not mention, I mentioned before, sea surface temperature, right? This is warmer. Red means warmer, blue means cooler. Warmer conditions means El Nino, cooler conditions means La Nina. El Nino, La Nina, these are Spanish words. Unusual activity off the coast of Peru in South America around Christmas time, December, end of December, around this time basically. When they see the sea surface temperature is abnormal, they call warm phase or El Nino setting up. And then, of course, opposite is the case for La Nina. When El Nino happens, it has disruptive rainfall events, not only in the US, it has impacts on the Indian coast also. So people have already studied a lot of things about this warm phase, cold phase of El Nino and La Nina, and see how it is impacting floods or droughts for a given region. So this is a climatology setting that I am talking about, hydroclimatology setting for rainfall producing events. But hydrometeorology event is the one that we are going to be looking at from that video. So those are two things that we need to be understanding. This literature is plenty. They are available for you to refer, but I want you to take away that these are the indices commonly people use when they talk about climate systems, El Nino, La Nina. So this is again a different rendition. Normal conditions, you have, of course, ocean surface heating, as we know, happens all the time. But abnormal heating brings rainfall, heavy rainfall, and cooling brings low rainfall. So that part you need to remember in general. Implications for India for El Nino conditions and southern oscillations combined, ENSO, brings more rainfall for India. La Nina brings less rainfall. Again, if drought setting happens in India, for example, you may want to look at what kind of climate indices that India is going through, whether it is in the warm phase of El Nino or La Nina or cold phase of El Nino or La Nina. So those kind of, and then the other one other index that I want to talk about is Indian Ocean dipole. It's another index that are directly related to heavy rainfall producing events for Indian Ocean. It's basically a clockwise circulation of moisture, unusually warm water. Under normal conditions, Southeast Asia gets this rainfall. If IOD, Indian Ocean dipole, is normal. But if it's in the warm phase or positive phase, coast of Kerala or western India basically getting warmer conditions and more rainfall to the west of India, including India. But then if it is in the negative phase, you have cooler conditions on the coastal part of India, western coast, but then it brings more rainfall to the far east, not India. So we may see drought settings here, we may see flood settings here. So flood and droughts are also kind of indirectly connected to the circulation patterns that we see. And in that video, you will see how they are talking about the jet stream. One part of the jet stream get disconnected and moving directly over Asheville or over Valencia in Spain, and how that supplies moisture. So those are the general things that you need to understand. So what we have done so far is to understand the rainfall types of, what kind of budget that we want to understand with respect to water cycle, and then see how peak flows are going to be translated based on the watershed conditions, and how to quantify that generally speaking, and the return periods and design storms that we talked about, mesoscale hydroclimatology, hydrometeorology setting, and we ended up with this ocean circulation. This is again a very cursory approach to understanding flood modeling. I have not even gone into the depth about flood modeling. We will see a case study. I will also post the papers to you for this class. Two examples. One is using machine learning based. I could actually go over that quickly, and then we will share the video. Oh, the last one is about Arctic polar vortex that I need to give you an introduction to. So this is happening in the US right now. Basically, climate warming is happening in Arctic, right? So these vortex are the cold air mass that is getting broken because of climate change. That's another interesting research that's going on currently. But these jet streams, right, are closer to the Arctic pole in the winter. I mean in the summertime, but then it comes down in the winter. That's why it brings cold air mass to the majority of the areas. And the warm air is coming from the south, cold air, and then it pushes this jet stream. Actually, the shape of the jet stream is broken by this warm air coming from the south, from Mexico, from South America, excuse me, from the equator. But this shape determines how much cold air we are going to get, and then ocean heating brings the moisture, and where we are going to have snowfall in the US is primarily driven by this polar vortex process that we see every year. Okay, I'm going to stop here and then see if I can show the video before we conclude for today about my lecture. But then if we need to come back to this lecture later on, I mean, I have to see that case studies part. Are we meeting this afternoon here before the tutorials? Or if so, then I can show the case studies of India in the afternoon. I don't need even 1 hour, maybe half an hour, 45 minutes. Then we can go to the lab. Is that okay with all of you? Okay. Yeah. So then in that case, I will, until the next speaker comes, I am going to present the video. Now when you watch this video, look at it with a different eye. You know, we talked a little bit about jet streams. We talked about how the rainfall should be partitioned, what kind of peak flows that we are going to have. So can we play the video now?
The flash floods smashed through buildings, swept away vehicles, and destroyed roads and bridges. In the hills, the rain triggered landslides that buried homes and cut off roads. As the search begins for the missing, people want to know, why did this happen here and now? This was not the first time Asheville flooded. In July 1916, the tail end of a hurricane hit western North Carolina, followed by another hurricane 9 days later, dumping heavy rain on the city. The resulting flood killed about 80 people. It became known as the Great Flood of 1916. Despite its mountain location far from the coast, Asheville's geography actually makes it vulnerable to floods. Parts of the city run along valleys, close to the French Broad and Swannanoa rivers. And the mountains around the town help generate rain.
For example, same setting.
Western North Carolina, upstate South Carolina, it's got a unique feature called the Blue Ridge Escarpment. The terrain rises very rapidly. So you have this air that's being lifted up against the Blue Ridge Escarpment, and as the warm air rises, it condenses and it starts raining. And it just all starts routing down from this creek to this creek to this creek. Eventually, the larger streams start rising. And this is where they live.
This landscape helped create the Great Flood of 1916. But the flood of 2024 was even worse. In Asheville, the Swannanoa River peaked over 5 feet higher than the level reached in 1916.
Nobody in this part of the country that's alive has ever seen anything like this before. It was devastating.
So why was this flood so extreme? A clue comes in the form of another disaster on the other side of the Atlantic.
Now we are going to Spain, Valencia.
Just a month after the floods in North Carolina, a deadly storm hit Valencia in Spain. Like Asheville, Valencia is a popular tourist destination.
It is
But
not
the landscape
same
here
as
is
Kerala
different.
or
The
Asheville.
city sits between low-lying mountains and the sea. Rain is rare. The ravines that run through the nearby towns are usually dry. But when big storms occur, they have been known to flood. October 29th, 2024. Meteorologists across Europe are growing concerned about an approaching weather system.
This was going to be an extreme event. This was going to be dangerous. This was going to be something that was going to have a high impact for the people in the region. By the morning of Tuesday, the 29th of October, a red warning had been issued at about 7 a.m. Red warnings mean that there is a danger to life.
On Valencia's coast, a strong wind whips up the Mediterranean Sea. But there's hardly any rain. However, inland, heavy rain is falling in the hills and collecting in valleys. Just south of Valencia, a ravine called the Rambla del Pollo runs from the mountains toward the Mediterranean. Over half a dozen communities, including the town of Paiporta, line its banks. More are dotted in the surrounding floodplain. Over 200,000 people live along the ravine.
This is the flash flood.
Shortly after 2 p.m. local time, water flowing down the Rambla del Pollo reaches the town of Paiporta. It carries a wave of debris. Within a few minutes, the dry ravine becomes a powerful, fast-flowing river. In the afternoon, the rain in the hills intensifies rapidly.
During the height of the storm, one location recorded 771 millimeters of rain, which is about 2.5 feet of rainfall, falling over a space of 14 hours.
Shortly after 5 p.m., flash flooding engulfs a town near the top of the ravine. At 6:28 p.m., in Paiporta, the river overflows its banks and rapidly floods the streets.
All the neighbours in the entire area started bringing their cars up out of the underground parking. That was very strange.
This rapid uplift generates huge thunderstorms.
Have sustained moisture flow and the dynamics associated with a cutoff low that leads oftentimes to extreme rainfall.
Okay, so I may
In
have
North
skipped a
Carolina,
bit.
the heavy rain that pummeled
So I want to
caused rain
show
to
this
fall in
important
Spain.
part here. I think I mentioned the jet streams before, right? And the low pressure, high pressure zones. So this is the connection that what I wanted you to see
During a
here.
12-hour period. What caused so much rain to fall in such a short time? The answer is a weather system meteorologists call a cutoff low. A cutoff low can form when an area of cold, low-pressure air gets cut off from the flow of the jet stream. This high-altitude rotating mass of low-pressure air can draw in moist air from below.
The fact that they are cut off from the main flow in the atmosphere means that they sit in one location and pump moisture into the same region for several hours to days, even up to a week.
When cutoff lows interact with a plentiful supply of moist air, such as a warm ocean, they can become dangerous. That summer, the Mediterranean Sea reached record high temperatures.
You have cold air in this cutoff low, but the Mediterranean waters were quite warm. That leads to a very unstable atmosphere that can produce rising air, condensation, and a lot of rainfall ultimately.
Beneath the cutoff low, warm, moist air at the surface rises rapidly, drawing in more warm air, full of water vapor, from the Mediterranean. This rapid uplift generates huge thunderstorms.
Have sustained moisture flow and the dynamics associated with a cutoff low that leads oftentimes to extreme rainfall.
So that is the crux. of that.
And with the added push
I will
of that-
stop.
Helene was
I will
overall
stop at one
increase in
point
flooding,
here, but start again
especially
on
in the
landslides
east.
because they will actually move. Of course, the same scenario they talk about in Asheville, North Carolina. The cutoff flow they're talking about, is coming from the jet stream that's moving to the south and getting locked up in a system, getting moisture supply from the ocean, and then adding into the circulation. That causes the flood producing rainfall event. So I think the timing is so correct now that we can stop at this point for a shift from here to use of AI and climate studies. Um, okay, okay then. But that is done by you. Okay, Dr. Satish. Okay, Dr. Satish Kumar will be talking about that today. But then we will continue little bit about the connections between what I said about Indian context and how these climate indices can be impactful for India. Monsoon rain, which brings 80% of our rainfall quantity for 70 to 80% of the land mass of India. Very important to understand these ingredients of heavy rainfall producing events. Instead of just looking only floods at a local scale, you start from bigger picture and then down, scale it to a point where you want to look at it. So I want to kind of give that overall holistic view. First of all, I'll stop here. And Dr. Satish Kumar, would you like to come and continue this lecture on satellite data processing? Is that it? Use of satellite for understanding. Again, a very important topic, as you can imagine. Without data, there is no hydrology. Without data, there is no understanding of these extreme events, right? But very difficult to go and collect the data for every location. So satellites are very helpful to really bring that gap into a reality for us to fill in those gaps with satellite data. It's used in different contexts, but I let Professor Satish Kumar to come and continue the lecture. Thank you. We'll see in the afternoon again. Continue this conversation with this video. I'll close this video for now. Is that right?